Dr. Dawes here. I'm going to talk about Hertzsprung-Russell diagrams, which are the tool we use in Lab 4 to study stars. Hertzsprung-Russell diagrams, they're an amazingly powerful tool for analyzing and understanding stars. They were invented by these two gentlemen, Hertzsprung and Russell, around 100 years ago, in the early 20th century. And let me just write the words down here in my somewhat sloppy stylus writing. For short, we can just call them HR diagrams. All right, so we need to look at what they are, how they depict properties of stars, and how with just two variables, a graph that just shows two data for each point on the graph, we can figure out an amazing amount of stars, how they exist, how you could say how they live, how they die. A lot of that comes out by examining Hertzsprung-Russell diagrams. So that's what we're going to do in Lab 5. Let me erase this and sketch the outline of what a Hertzsprung-Russell diagram shows, because it takes a little bit of practice. And then you're going to be plotting your own data points, if you haven't already, for Lab 4. You should have that done before Lab. All right, yeah, clean enough, because you don't want to watch me erase things. So, in a Hertzsprung-Russell diagram, you just have the two usual axes that you get in a Cartesian graph, an XY graph. So I'll just sketch a couple lines for the axes. And then what Hertzsprung and Russell started out with, and it's still typically commonly the way it's done, is the horizontal axis, the bottom line, is the spectral classes of stars, O, B, A, F, G, just the standard common spectral classes, GKM, OB, AF, GKM. Another way you can think of it is this is temperature, but of course if you're going to think of it as temperature, keep in mind that it gets hotter to the left. The O stars are by far the hottest stars. Those are the blue-violet ones with their continuous spectrum of black body type radiation. They put out most of their visible light radiation at the short wavelength end of visible light, which is the blue and violet end. So it gets hotter to the left if you want to think of this as a temperature scale, and we could label it as a temperature scale instead of a spectral type scale. And then off to the right, the M-type stars, those are the coldest, and their continuous spectrum emitted as if they were black bodies is putting out a lot more in the red long wavelengths, which is lower energy, longer wavelength. So those are red stars. So you go from these blue, violet, O and B stars to these red, M, and K stars, and then yellow and orange colors in between. All right, the vertical axis is, in simple terms, it's the brightness, okay? Getting brighter towards the top. Brightness. One way to measure and depict on a graph the brightness of a star, of course, is in magnitude, invented by Hipparchus. The thing to keep track of with magnitude is that the higher the number, the dimmer the star, the less bright it is, because when Hipparchus came up with the scale, number 1 magnitude was the brightest, number 2 less bright, number 3 on down from there. If you're talking about apparent visual magnitude, what we can see from Earth with our naked eyes, the brightest stars are up around 1, or between 0 and 1 actually, with a more precise modern version of the scale. The dimmest you can see with the naked eye is down around 6. So if it's got a number greater than 6, that is dimmer than 6, you wouldn't be able to see with the naked eye in terms of apparent visual magnitude. Now if we're talking absolute visual magnitude, then that's how bright it would look as seen from Earth if we could line it up a distance of 10 parsecs, not quite 33 light years away from Earth. So you might see the vertical axis labeled absolute magnitude, that's capital M, italicized subscript V. Or you might see it apparent visual magnitude, small m, subscript V, depending on how it's going to be depicted for that particular Hertzsprung-Russell diagram. Another way to depict brightness, let me go back a step. If you're going to do absolute or apparent visual magnitude, this is absolute, just to remind you that going up higher on the graph, it gets brighter, therefore the magnitude numbers go down to smaller values. So your axis might run something like this. and it gets dimmer this way and brighter towards the top, even though the numbers seem to go backwards. That's how magnitude works. So keep that in mind. The numbers get bigger going down, not going up, when you're using magnitude for your brightness gauge. Okay, and then another way to do it, I'll put it over here on the right, is you can use solar luminosities as your brightness unit. You can also use watts, just like a light bulb, but a star puts out so many watts, 10 to the 26th, 27th, 28th power, depending on how bright the star is. Those are too big a numbers to work with. I mean, that's not usually used, even though we could use wattage. Instead, what's commonly used is consider the sun to be our standard light bulb. Then how bright is the star relative to the sun in terms of its actual brightness at the source? So the sun would have a solar luminosity value. That dot's supposed to be in the middle. The symbol for the sun is a circle with a dot in the middle. So this is a capital L for luminosity, subscript, the symbol for the sun, circle and dot with a dot in the middle. Those are solar luminosities. One solar luminosity equals the brightness of our sun. And then it's usually done logarithmically. 0.1, 1/10 the brightness of our sun. 0.01, or actually you'd write 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. And we're getting down to pretty dim stars at this point. 10 to the 1, 10 to the 2, 10 squared, etc. So this is a solar luminosity scale. So that's three different ways you can label the vertical axis as absolute magnitude. In some contexts, you could even use an apparent visual magnitude instead. But for the most part, in general, you're going to want absolute magnitude. And that's what Hertzsprung and Russell did originally. And then another way to do it is in solar luminosities. Here's a symbol for that. How bright it is relative to our sun. Or you could just use watts, but that's rarely used because that's not real useful for star brightness. They're too hot to be a standard, to be thought of as light bulbs. Okay, that's enough for how Hertzsprung-Russell diagram axes are labeled and what the units mean. Thank you.